Dakota, not to see you. Please turn on your Zoom camera. James, William T, Carson. Who is recording? Max who? Okay. Now we want to continue with the chapter 5, integrals. Okay. Remember, we have learned how to find antiderivative, right? And in section 5.1, we also learned how to deal with the area by dividing these into a lot of small rectangles, right? We use the rectangles to approximate the area underneath the curve, right? Between A and B, and the curve y to fx, okay? The idea is so-called divide and conquer, right? You divide AB into a lot of small subintervals, right? For every subinterval, use rectangles to approximate the area, right? Because everybody knows how to calculate the area for rectangles, right? Now you take the limit as n approaches infinite. What does n mean? N is the number of subintervals, right? So the idea is so-called divide and conquer method. The idea is very simple, right? You divide this into a lot of subintervals, and you use rectangle to approximate, then take the limit as n approaches infinite. You will get the exact area, right? Now, all these can be summarized as what? As the integral from a to b of fx. Remember the notation? This is integral notation, right? From a to b fx dx. If fx is non-negative, then the meaning for this integral is the area under this curve between a and b. Right? Now let me share the screen. Okay, share the screen. Okay, you can see the screen, right? Now we are in chapter 5. Okay, we're in chapter 5. You can see the screen, right? Now we are in section 5.2, at least, I think, right? This is so-called the definite integral. See, evaluating integrals, right? How can we evaluate, right? So far, we have learned the definition, so-called by using so-called the limit of the Riemann sum method, right? So in this case, you have to remember these summation formulas. Remember, this is the sigma I from 1 to n. This is sum of first n natural numbers, right? It's given by this formula. Okay. This is the sigma of I squared I from 1 to n. Sigma means sum. Okay. This means the sum of first n perfect squares, 1 square plus 2 square until n squared, right? The formula is given by this. You can prove this by mathematical induction, right? Now you have third formula, which is this. Okay, that means what? The sum of first cube powers, right? 1 cube plus 2 cube plus 3 cube and n cube. So what's the formula, right? Right? It's n times n plus 1 over 2, the whole thing squared. Okay? So why we want to use this formula? Because in this section, we must use these formulas to evaluate the integral. Okay? By using sigma notation. Sigma is nothing but the sum, okay? So this is the properties of sigma. I have summarized this last time, right? So this is, okay, this is that. Now let's do one example here, okay? Let's look at example 2. Evaluate the Riemann sum for fx equal to x cubed minus 6x. This is a cubic function, right? X cubed minus 6x. Now you have taken the sample points to be right-hand points, and starting with a equal to 0, b equal to 3, n equal to 6. What does n equal to 6 mean? You have to divide this interval 0, 3 into 6 equal parts, right? Now you have to evaluate the integral from 0 to 3, x cubed minus 6x. Okay. First, let's evaluate the Riemann sum for this integral, for this function, okay? So the Riemann sum is very easy to evaluate, right? This is first, you want to find n equal to 6. Now the interval width is what? Delta x is total length b minus a over n. A is 0, b equal to 3, right? So b minus a is 3 minus 0 over 6. It's 1/2. Okay, now you can, it's very easy to find out all these things, right? You have 0, 3. Okay, this is 0, right? And this is 3. Okay, you divide this into 6 equal parts, right? So let's say this is 1, this is 2, this is 3, this is 4, this is 5. 1, 2, 3, 4, 5. So not very nice. So let me just erase that. Let me do it again, okay? From 0, this is 0, right? And then this is 3. Okay, so this is 1/3. Right, this is 2/3. Now this is half 1/6. Right, this is another 1/6. Now this is much better, right? See, you divide this into 6 equal parts, right? So for every part, the length is what? Is 0.5, 1/2, right? So you can find this is what? 0.5, right? 0.5, because the yellow part is 0.5 is 0.5. 0.5 plus 0.5 is 1, right? And this will be 1.5. And then this will be 2, right? And then this will be 2.5. Common sense, right? Because the delta x is 0.5, right? Is 0.5, right? So therefore, you can find the what? The coordinate for each interval, right? 0 plus 0.5, 0.5 plus 0.5, which is 1, 1 plus 0.5, 1.5 plus 0.5, 2 plus 0.5, and 2.5 plus 0.5, right? So you can find all these values, right? See here. This is this number is called x0, right? And this will be x1. And this will be x2. And this will be x3. And this number will be x4. And this number will be x5. And the last number will be x6. Okay, now you can find all these intervals, right? x0, x1, x2, x3, x4, x5. See here, right? See here. Okay, right? x1 is 0.5, so on and so forth. x6 is 3, right? Now you can what? You can find the Riemann sum. Okay, Riemann sum is by instruction. You have to use what? The right endpoints, right? So that's R6. Okay, Rn, R6, because n equal to 6, right? R6 is given by this sigma sum, right? F, you choose the right endpoint as height, right? The right endpoint is fxi, okay? Right? Times the base, which is delta x. Okay? Then I from 1 to 6. Right? That's the Riemann sum, R6 equal to sigma I from 1 to 6, fxi delta x. Now you put this number inside, you can evaluate, right? So let's take a look at the textbook. Okay? Now it's easy to evaluate. Put this number inside, right? Fx1 will be 0.5. Delta x plus fx2 will be 1, right? Fx3, f1.5. You have 1, 2, 3, 4, 5, 6. You have 6 terms, right? Now put this number inside function to evaluate that, right? And divide by delta x is 1/2. You can put outside, right? So the answer is this. Okay. So R6 is given by negative 3.9375. Okay, so R6 is this number. Okay, so this is called what? Riemann sum with n equal to 6. Okay, with n equal to 6. With the endpoints to be the, with the point to be the right endpoints for each subinterval. Okay, so this is our R6. Now, what's next? We have to evaluate. Look at the picture here. This is the graph for x³ minus 6x between 0 and 3, right? You divide this into 6 subintervals, right? 6 subintervals. Now you can look at that. We use the right endpoint as height, right? So at this, we use this as height. And here we use this as height, right? And for this subinterval, we use the right endpoint as height. For the fourth subinterval, we use the right endpoint as height. For the fifth subinterval, we use right endpoint as height. And for the last subinterval, we use the right endpoint as height. Okay, so you can see that here is what? Negative, 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 negative. This is positive, right? Because this is negative side, right? The base is always 1/2, it's positive, but here the height is negative because it's on the negative y side, right? So the answer is negative something because you see the positive part is smaller than what? The negative parts, right? So therefore, R6 turns out to be what? Turns out to be a negative number, right? Negative number. Because the picture is not entirely above the x-axis, right? The picture, part of that is under what? Positive, under the x-axis, and part of the curve is above the x-axis, right? So you have negative y value and you have positive y value, right? So you look at the picture, it's very clear why R6 is negative here, right? Negative here. Now let's evaluate the integral from 0 to 3, okay? Now, in order to evaluate the integral from 0 to 3, you have to what? You have to divide this in with n subintervals. Then take n go to infinity, right? So delta x is this. B minus a over n. N is any positive integer. N can be 1 million, n can be 6, n can be 1 billion, n can be 1 zillion, right? Anyway, n can be a huge number, right? Because finally, you have to take the limit as n go to infinity, right? So B is 3a 0, so 3 over n, right? So these are delta x. Now, x0 is 0. x1 is 0 plus 3 over n, which is 3n. x2 is 0 plus 2 delta x, so 6 over n. x3 is 0 plus 3 delta x, so 9 over n. So in general, xi is, remember, that's how to find xi, right? xi is given by the formula, right? xi is x0 plus, copy down, okay, I delta x. This is formula for xi. Okay, so xi, this is xi, okay, is given by x0 plus I delta x. Now x0 is 0, right? I is index, and the delta x is 3 over n, right? So simplify that, you'll get 3i over n. Okay, here, see, right? Nice, right? We have found that xi equal to 3i over n by using the simple formula. Right? Now we use what? The right endpoints. Okay, so we can use what? The limit of this integral is the limit of the Riemann sum. Right? Limit sigma I from 1 to n f xi is 3i over n, delta x is 3 over n. Now you have to evaluate this sigma and then calculate the limit, evaluating the limit, right? Now it becomes pure algebra, right? It becomes pure algebra. Let's do it step by step, okay? Let me enlarge it for you, okay? Okay. You can see it, right? I hope, okay? So limit as n approaches infinity, 3 over n has nothing to do with index I. You can put outside, okay? Now inside is sigma I from 1 to n. I cannot scroll down. Why? Let me see why I cannot scroll down. Okay. Okay, I see why. Okay. Can you see it? Yeah, I see. Okay, let's see it very clearly, okay? I want you to see it very clearly. Okay, now, okay, now, okay. Something wrong.
I think.
Okay, now you can see it. Can you see it? Can you see it?
Oh, there we go.
Let me, I want to enlarge it. Now, I don't know why this happens.
I mean,
Okay,
you don't
good.
have to zoom in if it's going to be too difficult for the zoom.
Now you want to evaluate this, right? Now you want to limit. You want to take the limit. Oh, now I see. Okay, now take the limit for this Riemann sum, right? Now you put fxi is 3i over n. We have just computed, right? Delta x is 3 over n. Okay. Now see that 3 over n has nothing to do with index I, so you can put outside sigma sign. Okay. So limit 3 over n. Sigma inside is sigma I over n. So what's f? Remember, is x cubed minus 6x, right? So replace x by 3i over n. You have cubic power minus 6 3i over n. Okay. This is just evaluating function f. Okay. Now you have to what? To do some algebra, right? So limit as n approaches infinite, 3 over n, right? 3 over n is the what? Is your delta x, right? Now compute that. 3 to the power 3 is 27. IQ over NQ minus 6 times 3i is 18i over n. Okay, so this is pure algebra, right? Let's continue. Okay, let's continue. Okay, let's continue. Okay, now you have these, right? You have these. 18i over n. Okay. Now you what? You can distribute, right? Distribute. Okay. Now how to distribute? Sigma I from, because this is different, you can distribute, right? 3 times 27 is 81. N times NQ is N fourths, right? So you can do that. Let me show one more step, okay? One more step. This is equal to limit as n approaches infinite, right? 3 over n. You can what? You can distribute sigma sign inside because it's in negative, right? Different. Is equal to sigma 27 NQ over NQ, right? And times IQ minus sigma distribute 18 over n, 18 over n, I, okay, I. So sigma is I from I to 1 to n, right? This is also I from 1 to n. Right, now you can see that 27 over NQ has nothing to do with index I, you can put outside, right? So it's equal to the limit and n approaches infinite, right? 3 over n. 27 over NQ times the sigma IQ, right? Here, 18 over n has nothing to do with index I, you can put outside. So it's 18 over n, sigma I, okay? Right, now you can what? Distribute 3 over n inside, now you have these, right? Limit n, 3 times 27 is 81, n times nq is n fourth. Sigma IQ minus 3 times 18 is 54. n times n is n squared, right? Sigma I. Okay, so you have to use these two steps in order to get here, right? Get here. Okay, get here. So now you can what? You can apply the formulas for sigma IQ and sigma I. Remember, right? So we have. Okay, we have these two formulas. Limit as n approaches infinite, h1 over n fourths. Remember the formula is n plus n times n plus over 2 squared. Minus this formula is n times n plus over 2, right? So you have to evaluate this limit, which is very easy now, right? Limit as n approaches infinite, 81, 2 squared is 4, right? So 81 over 4. Now these you put n fourths inside, right? So you have n times. Why you have this? Let me show you one step, okay? The book omits this step, but it's easy to see, okay? Put n fourths inside. You have n plus 1 squared, n squared over n plus 1 squared, right? Over n fourths, right? You cancel out n squared, right? So it becomes n plus 1 over n squared, right? Plus square for total thing, right? So n over n is 1, 1 over n is 1 over n. So you have this square, right? Minus 27, here you can cancel n, see? Cancel n, right? So it becomes what? Becomes n plus 1 over 2n, right? Put n here, okay? 2n. Now you can what? N over 2n. Okay, 54 over 2 is 27. So this is, right? This is 27, okay? Now n over n is 1, 1 over n is 1 plus n, right? So we have this, okay? Very nice. Now you can what? Compute the limit as n approaches infinite, right? See? Right? We're almost done, right? You calculate this limit as n approaches infinite. So this go to 0, this go to 0, right? So you have 81 over 4, because this go to 0, right? 1 squared 1. So this go to 0, minus 27. 4 is the common denominator, so the answer is this. Okay? Negative 6.75. Okay, so we have found the integral for this, right? See, it's negative 6.75. It's quite long, right? But the idea is very simple. You use the limit of the Riemann sum method to get this number, right? The answer is negative 6.75. Okay, see, look at the notes here. In the sum, n is a constant, unlike I, right? So we can move 3 over n in front of the sigma sign, right? So remember that, okay? Now we have, look at this, look at the picture here. 0 points from 0 to 3, right? X cubed minus 6x is what? Is the net area, not the total area, but the net area, right? This is positive area, this is negative, right? So the net area will be negative 6.75. Not the total area is what? You add z plus z's, right? The total area will be positive, right? But this is called the net area. Sign is included, right? This is negative sign, this is a positive sign. You can see that negative is larger than positive, right? So this is negative 0.675. Okay, because the graph is what? Under x-axis and above the x-axis, right? So this part will be negative, this part will be positive, right? So you add them together, you will get negative 6.75, right? So this will be so-called the net area, right? Net area. Okay. So this is what? This is by using R40, right, to approximate, right? You will get about this, right? So this is approximation. See, when n equal to 40, you get this number, R40. And n equal to 5,000, you get R5,000, right? So the answer is what? Closer and closer. Remember, the exact answer is negative 6.75, right? If n equal to 5,000, you will get R5,000 equal to negative 6.74. It's very close to negative 6.75, right? So what if n is very large, you will get a nice answer, nice approximation. Okay. This is, you have to use computer algebra to because this is, but the Riemann sum is easy. Okay, this is the limit of the Riemann sum. But you have, in order to evaluate this, you have to use computer algebra. Okay. Now this is a picture for this part, right? You want to evaluate the area between 1 to 3 under this y to ex, right? So this is the answer. Now let's look at this. Number 4 is very useful. Okay, you want to what? You want to find, evaluate the following integrals by interpolating each in terms of the areas. Now let's do number 1. A, how to evaluate this? How to evaluate 0 to 1 square root 1 minus x squared dx. Okay, let's use the meaning for this. What does it mean? What does this mean, right? It means what? Function is y to fx, right? Is square root 1 minus x squared, right? And the interval is from 0 to 1, right? Interval from 0 to 1. Right? Function is from square root of 1 minus x squared, interval is from 0 to 1. Now you can see that, you can what? You can square both sides, right? So y squared equal to 1 minus x squared. Move next x squared to the left side, you will have x squared plus y squared equal to 1. Now this is what? This is a circle, right? This is a circle with radius 1 and centered at 0. So you can draw this picture very easily, right? But this is not the full circle, it's only the half of that. Y is only half of that because y is positive, right? Right? Because y equal to square root of 1 minus x squared, y is non-negative here. Right? So this is not the full circle, but only the top half. Now the interval is from 0 to 1, right? So this meaning is what? The area of this. So this is the area of the core circle, right? The area of core, because the interval is from 0 to 1, not from negative to 1, okay? From 0 to 1, right? So this means what? This number is what? Is the area of this circle, right? A quarter circle between 0 and 1. Now you can find this answer very easily. The full circle, the area is pi r squared, right? The radius is 1. This is a quarter of that, right? So it's 1/4. Okay, so we have found the answer. The answer is equal to pi over 4. We can find the answer very fast because this is a circle. We know how to find the area. If this is not circle, then this method will not be useful because the area will not be easy to find, right? Since this is a quarter circle, the area is pi over 4, easy to find, right? So we have found the answer to the first one is pi over 4. Okay, let's take a look at the answer in the textbook. I hope we have the same answer. Right, pi over 4. See, pi over 4. Right, pi over 4. Okay, now let's do the second one. Find this. Find the integral from 0 to 3 x minus 1. How to find it? By using the same idea, by what? By linking this to the area, right? Because this area is easy to find, so you can use this method. If area is not easy to find, this method will not be very useful, right? So first, you sketch y equal to fx equal to function is x minus 1, right? Interval is from 0 to 3, right? Okay, now this is what? This is a line, right? A line, because y to x minus 1 is a line segment, right? A line segment. The interval is finite, right? Let's sketch this line, okay? x equal to 0, y equal to negative 1, right? Y equal to negative 1, right here, right? You see, x equal to 0, y equal to negative 1. X equal to 3, y 2, right? 1, 2, 3. So y 2 right here. Now this is the line here. Right? This line. Okay, this line. This is 3, right? And then this is 2. Right, this is 2. Okay, this is 2. Now how can we evaluate this integral? Remember? This is y equal to x minus 1, right? Between 0 and 3, right? This is right. This is line segment between 0 and 3. Y equal to x minus 1, right? X equal to 0, y equal to negative 1, x equal to 3, y 2. So this is a line segment. Now, how can we evaluate this integral? Remember the meaning for this? You have to find what? The area of A1. So this is A1, okay? A1. And then this is A2. A1 is negative and A2 is positive, right? So you can what? Add them together, right? A1 is what? Is the area for this rectangle, right? So A1 is equal to the area, okay? Area is positive, right? It's 1/2. Base 1, height 1, right? It's 1/2, right? A2 is the area for this piece, right? What's A2? Is 1/2 base times height, right? What's the base? Base is, this is 1, right? Base is 2. Height is 2, right? Because this is 2, right? So this is 2. Now, how to calculate this integral? Remember, equal to negative A1, because A1 is underneath, right? So we have negative A1 plus A2, right? Plus A2. Okay. Why is negative A1? Because this graph is under this curve, right? Under x-axis. So you have negative A1 is 1/2, right? Plus A2. A2 is 2, right? 2. So the answer is 3/2. Okay, 3/2. Positive 3/2. Okay, so we have found. Nice, right? Because A1 is easier to find, A2 is easier to find because this is what? Right triangle. This is also right triangle, right? So the area for A1 and A2 are easy to find, right? Are easy to find. Now you can what? To get the answer by using negative A1 plus A2, right? Because A1 is on the negative y side, A2 is on the positive y side, right? So the answer is 3/2. Okay, 3/2. Let's take a look at the answer in the textbook. I hope we have the same answer. Okay, in 3/2, I hope. Now this is for part 1, right? This is a quarter of a circle, right? A quarter circle. See, right? Same answer. 1.5 is 3/2, right? It's 3/2. Okay, it's 3/2. Right? Our answer is 3/2. This is 1.5. The same thing, right? See? Look at the picture. Right? Look at the picture. This is A1. This is A2, right? A2 is negative, A1 is positive, right? So A1 minus A2, right? You get 1.5, right? Y equal to x minus 1 is a line segment between 0 and 3, right? So you have to find the area for this piece and the area for this piece. A1 minus A2. Why A1 minus A2? Because what? Because A1 is positive side, A2 is negative side, negative y side. What's the total area? The total area is what? A1 plus A2, right? But this is what? This is the net area, not total area, right? Total area is positive, right? It's A1 plus A2, it's total area, right? But this integral is the net area, including the sign, right? So A1 is positive sign, A2 negative sign, so you have to use this minus this, right? Easy, right? Easy. So remember, okay, The integral is not the total area, but the net area. Okay, the net area. Okay, so we have finished these 9 sections. Okay, 9 sections. Okay, that's the. Now the middle point rule is just using take the what? Take the xi to be the 1/2 of the middle point. Okay, this is not very difficult to understand, right? Remember, we use ln, we use rn. We take the left end point and the right end point, right? But you can take any point you want inside each subinterval, right? So here, xi bar is the middle point. See, xi bar is the middle point of the subinterval, right? So 1/2 left end point plus right end point. Okay, so this is easy, right? Easy. So you can use left end point, you can use right end point, you can use middle point. Actually, you can use any point inside this as your height, right? Okay, so I don't want to go over that because this is too easy, right? Too easy. Okay, too easy. Okay, next. Now let's take a look at the properties of the definite integral. So what's the property here? Let's take a look at the video first. Take a look at the video first. Okay. Yeah, we have time, a lot of time.
We just saw that the area under a continuous curve can be approximated by the sum of the areas of rectangles. This sum is called a Riemann sum, named after the German mathematician Bernard Riemann from the mid-19th century. Take the limit as n goes to infinity of the Riemann sum. And this is equivalent to adding up the areas of an infinite amount of rectangles under the curve. If this limit exists, then we have the exact area under the curve. This limiting sum is called a definite integral. And here is the notation we use for the definite integral of f from a to b. F is a function defined for x values from a to b. Divide the interval ab into n subintervals of equal width delta x. Each xi star represents a sample point in each of the n subintervals. So for each rectangle, we have a height of f of x I star and base of delta x. If this limit exists and gives the same value for all possible choices of the sample points, then we say that f is integrable on the interval ab. The elongated s in the notation for integral is called an integral sign. F of x is the integrand, and a and b are called the limits of integration. The dx simply indicates the independent variable is x. The procedure of calculating an integral is called integration. There's one more thing I should mention, and that's delta x is equal to b minus a over n. Notice, looking at our graph, this gives us an equal base length for all n rectangles. Next, we develop some basic properties of integrals that will help us to evaluate integrals in a simple manner. Assuming that f and g are continuous functions, we have the following properties. And all of these are derived directly from the definition of a definite integral we just discussed. For example, take a look at number 2 on our list. This says that an integral of a sum is the sum of the integrals. To show this, we write out the definition of the definite integral for f plus g. This is the limit of the Riemann sum of f plus g. We now distribute delta x and get the following. Here we have a limit of a sum, which we know from the properties of limits is just the sum of the limits, provided that each limit exists. But each limit does exist due to f and g being continuous. Here we now recognize that each term is its own integral. We can now see that property 2 is certainly true. Properties 3 and 4 can be proven in a similar manner. Now, let's apply some of these properties. If the integral of f from 0 to 5 is equal to 20, and the integral of g from 0 to 5 is negative 3, the following integral. We use here both properties 2 and 3. The integral of a sum is the sum of the integrals. And the integral of a constant times a function is a constant times the integral of the function. Next, we just plug in the given values for the integral of f and g. This gives us pi times 20 plus 2 times negative 3 equal to 20 pi minus 6. There is one more property I would like to cover, and that involves splitting up the integral in terms of its limits of integration. Here we have a graph where f of x is positive, but this property certainly holds for f of x negative. Keep in mind that when f of x is below the x-axis, we get negative values for the area between the curve and the x-axis. Splitting up this area under the curve at x equals c and adding up the area on the left with the area on the right is equivalent to what you can do when splitting up the integral. The integral of f of x from a to b is equal to the integral of f of x from a to c plus the integral of f of x from c to b. Next, we plot it. If the integral of f from 1 to 6 is 3.2, and the integral of f from 1 to 3 is negative 1.6, find the integral of f from 3 to 6. Here again is the property we'll be using. We need to first identify the limit of integration value c, which is between a and b. That c value is 3 in this case, because 3 is between the values of 1 and 6. So we have the integral of f from 1 to 6 equal to the integral of f from 1 to 3 plus the integral of f from 3 to 6. Plugging in the known values for 2 of these integrals gives us 3.2 equal to negative 1.6 plus the remaining unknown integral. So the integral of f from 3 to 6 is 4.8. As you can see, knowing the properties of integrals is essential when evaluating. Attempting these examples by directly applying the definition of the definite integral would be cumbersome and something we would like to try to avoid. You'll find these properties very useful when solving future integrals.
Okay, so the man just introduced some properties of the integrals, right? So let me scroll down, okay? These are the properties of integrals. You have first, c is constant, right? Its integral is c times b minus a. Why so? It's easy to show, okay? It's easy to show. When you have these, it's very easy to show, right? From a to b, right? A to b, okay? Here, y equal to c. Y c is constant, so the graph is what? It's a vertical, no, it's a horizontal line segment from a to b, right? This is c, right? Okay, now you want to find the area, right? Of this rectangle, right? Of this rectangle, right? Because this is the area for this, under this curve, which is the horizontal line segment between A and B, right? Now everybody knows how to find the area for each rectangle is base times height, right? The base is B minus A, the height is C. So we have this, right? We have this right away, right? By using what? The area for this rectangle, right? With base B minus A, the height is C, right? So therefore, you can find the answer right away is B minus A times C, right? Therefore, we have shown the first property, right? Easy, okay? Easy. Right? Easy. Next, remember the man just has shown this property, right? The integral from a to b fx plus gx is equal to the integral from a to b f plus the integral from a to b of g, right? So I don't want to repeat his demonstration. Now here, C. What does C mean? C here, part C, the property C is what? Here C is a scalar. You can put C outside, okay? The proof is very similar, right? C is any constant. Now what's property 4 mean? Property 4 means that it's very similar to property number 2, right? For the difference, you can distribute. You can do it term by term, okay? But remember, this is wrong, okay? This is wrong. So please do not make this mistake in the future. We do not have this property. Okay? From A to B, fx times gx. Somebody say, oh, that's so easy. Let's go to the integral from A to B of f x dx times the integral from A to B dx dx. This looks so tempting, right? It's very seductive, right? But unfortunately, that's wrong. Okay, that's wrong. So please note it down. It's very important. Do not make this mistake because that's wrong. Okay, for fx times dx, you cannot distribute. So similarly, this is also wrong. For A to B, fx over gx. Okay, fx over gx. Right? Somebody say, can do that? Do we have this nice property from integral from A to B, fx dx over the integral from A to B of gx dx. G. Do we have this? It looks so seductive, looks so tempting, looks so attractive, looks so nice, right? Naive. Wrong. Okay, wrong. So for product and for the product and for the quotient, we do not have similar properties. We have properties for what? For sum, right? For difference, but not for what? Not for product and not for the quotient. So please mark it down. So please mark this wrong. Please mark this wrong. This is a terrible mistake in calculus. Okay, we cannot distribute over the product. We cannot distribute over the quotient. Okay, only for sum, for difference, you can do term by term, right? But not for the product, not for the quotient. So please put this in your notebook, okay? Because this is a terrible mistake. This is also a terrible mistake. Even though they look very tempting, they look very tempting, right? But unfortunately, we do not have such naive properties. Okay, so please mark it down. Okay, because in the past, some people made these kind of mistakes, which was very embarrassing, right? Which was very embarrassing. So please do not make this kind of embarrassing mistake once more in this matter. Okay, because they are terribly wrong. Okay, they're terrible. Only for some. Remember, okay, only for some and only for difference you can distribute, but not for the product and not for the quotient, right? Clear. Everything is very clear now, right? Now you can do some examples, right? See, this is I have shown it for you, right? This is a rectangle, okay? This is the proof for part 2, right? By using the limit of the Riemann sum, right? The man have just shown it on the video, right? Video. Now you can use these properties to evaluate something, right? So how to evaluate? How to evaluate these? Number 6, use the properties of integral to evaluate these, right? This is sum. Remember, this is sum. So you can what? Distribute. If it's not sum, you cannot do that, right? This is sum. If it's sum or difference, you can do that, right? If it is not sum or difference, you cannot do that, okay? See, this is the distribute, right? From 0 to 1, 4 plus 3x squared. You can do it term by term, right? So 0, 1, 4dx plus 0, 1, 3x squared. Now, 3 is a scalar you can put outside, right? You have these. These are what? The properties of integrals, right? Now you can continue, right? Continue. how about this? From 0 to 1, 4 dx is, remember the property number 1, right? Is 4 times, this is C times B minus A, right? So it's 4. Easy. Now, how about this part? We have done this in the very beginning, right? We have done this because 0, 1 x squared dx is 1/3. Remember, this is the area of the what? Of the region under the parabola y equal to x squared between 0, 1. The answer is 1/3, right? So we have found the answer is 1/3. So this is 4 plus 3 times 1/3, which is 5, right? Because this is 1 plus 1. Okay, so we can find this by using, do not use the limit of the Riemann sum, just by using what? The properties of integral, right? You can find the answer right away. Okay, right. The answer 5. Okay. Okay. Next is this. The integral from a to c fx plus the integral from c to b of fx is the integral from a to b. Remember, the man have just shown this, right? The total area is what? Is this area plus this area, right? So this is very easy to show. Okay. See here, right? See, look at the picture. From A to C is the area for these, right? From C to B is the area for these. The total area is from A to B, right? So yes, that's that. Okay. Now, from 0 to 10 is 17. From 0 to 8 is 12. How to find from 8 to 10? By using this property, right? 0, 8 plus 8 to 10 is equal to the integral from 0 to 10, right? So you have found. So from 8 to 10 is this minus this, right? So 17 minus 12 is 5, right? By using the property, right? You can find the answer very fast, right? Very fast. Now here is comparison properties of integral, right? So this is, if fx is non-negative, if a is less than or equal to b, then the integral is also non-negative, right? Because why so? Because of the limit of the Riemann sum. fxi is always non-negative, right? So everything is non-negative, the limit is also non-negative, right? Now, if fx is greater than or equal to gx, then the integral is also the same. The proof is very easy by using the limit of the Riemann sum, okay? Now, this is fx is between m and n, okay? Then the integral is between, let's show it. Let's show property number 8, okay? Property number 8. Why have these? Okay, see fx is between two numbers, right? Lowercase m and capital M, right? So now we can use what? We can use the property of number 7, right? To find that the integral from a to b of f x dx is less than or equal to the integral from a to b m dx by using property number 7, right? And this is integral from a to b m dx, right? By using property number 7. Okay, now we learned how to find these, right? M is a scalar, so this is m times b minus a, see? Right, here m is a scalar, right? So this is m times b minus a. Okay, so we have shown these, right? By using the property number 7, we can find, we can show the property number 8, right? Which is this. Very easy to show, right? By using property. Property number 7 can be shown by using property number 6. The property number 6 can be shown by using definition of the limit of the Riemann sum definition, okay? Okay. All these, see, the property number 8 is, I have shown it for you, right? Shown it. Okay. Now you can use these to estimate. Use property number 8 to estimate from 0 to 1, e negative x squared dx, right? From 0 to 1, okay, from 0 to 1. from 0 to 1 e negative x squared dx. How to estimate this, right? Function is this function, e to the power negative x squared. The interval is from 0 to 1. So now you have to find what? This is a decreasing function. Why is this a decreasing function? Why? Tell me why. Why the function fx is e negative x squared is a decreasing function? It's so easy to understand because this is what? 1 over x squared. Right? Everybody knows that x squared is always what? Is positive function. No, is increasing function, right? Increasing function because the derivative is right for x positive, right? X squared is increasing. Okay, so this is x squared. Is an increasing function if x is positive. Okay, so 1 over that will be decreasing, right? So this is a decreasing function on this interval. Okay, so the maximum value will be e to the power the function is decreasing, right? So this will be maximal, this will be minimal, right? So the maximum value will be f0, the minimum value will be f1, right? So you have maximum value is 1, and the minimum value will be e to the power what? Negative 1, right? Will be e to the power negative 1. Therefore, by using the property number 8, we have this, right? This is the maximum value times 1 minus 0, and this is the minimum value times 1 minus 0, b minus a, right? So we can estimate, okay? We can estimate. Even though we don't know the exact answer for this, we can estimate this integral is between the two numbers, right? Between the two numbers, e to the power negative 1 and 1, right? So that means that you can use calculate to approximate, right? So this means that this integral is between the two numbers, okay? Between these. Even though we don't know the exact value for this, right? But we know that this integral is between the two numbers by using property number 8, okay? So we have finished. Okay, we have finished this section. Nothing more, I think. Right, this is the exercise, okay? So what time is it? Oh, 7:35, exact time, very good. 7:35, 7:35, 7:35, very good. So we have finished, okay? Very good, 7:35. Haha, please type your name before you leave, don't forget, okay?